Good afternoon, my dear students. So, this time we're going to talk about the basic set theory. This is one of the topics in discrete mathematics. Okay, so as I have promised the previous video, I will be giving you basic set theory as our second video for advanced math for ME, mechanical engineering students. So the first thing that we must know is the vocabulary and notation in knowing set theories. We will only be doing basics. So that's the delimitation. We will not go through a lot of it because there are still other topics that we have to know about advanced mathematics. If you like to master in set theory, then that could be one subject. For now, we're going to just do the introduction or the basic that you must know at this point in time. Okay, so the set vocabulary and notation. Set, this is an unordered collection of objects. So what I have here is a set of B such that this set has got the elements Eric, Adam, and Kevin. So you have a set B wherein it contains names of three persons, Eric, Adam, and Kevin. You call EAK or Eric, Adam, Kevin as elements. So a set must have an element. And if you define element, then you have to use a C with a dash at the middle. And not an element is a slash of it. Now, the statement that says Adam is an element of B is correct. A is an element of B or set B is correct. Why? Because A contains set B. Larry is not an element of B because you cannot see Larry in the set. B only has EAK, but it does not have L. Okay, let's move to the next slide or next part. Well, this is just to introduce some notations like in, like this with a double line at the side. That is what you call natural numbers. And natural numbers are all numbers from 0 or less than 0, which includes decimal, and to infinity, where in between has decimal numbers. And the whole numbers will be, we know it, we have the whole integers. These are counting numbers or natural numbers, okay, and including 0. And Z is defined as the integers. Integers has got positive and negative signs. So it's W with a double slash there. Or sorry, W is for the whole number and Z with a double line inside. But this is not our concern at the moment. But we need them when we are defining or we'll be using them in our set notation builder. So again, for integers, you have positive and negative. For whole numbers, will just be from 0 and the natural numbers. And natural numbers are all counting numbers without decimals. And then we have the rational. The rational will include the decimal numbers. Okay. And the real numbers will be all decimal, repeated, and ending the real numbers would include non-repeated or repeated numbers, decimal places, with decimal places. And complex numbers are those with an I. Okay. BI is an imaginary number. um, Square roots of negative numbers are imaginary numbers, and there are ways to treat them, to operate them, and we will deal with them as well as we go along. Right. Now, let's do the set notations. If you read this notation here, it says set, I'll use the white one. This is set of S, where elements are 1, 2, 3, 4, 5. We have what you call a roster notation. It has inside discrete sets, or they are countable, like 1, 2, 3, 4, 5. They are countable. And if you contrast this with continuous, then you say X, all elements, and we call them X's. All X's will be greater or equal to 0, which means there could be decimal numbers in between, and less than or equal to 1. So what are those numbers that are greater than 0 and less than 1? So you only have 0 and 1 in between as a whole number, yeah? And 0 to 1 could be 0 0.001, 0 0.5, 0. For as long as it doesn't reach 1, all the decimal numbers will be the set of X's. And that's the continuous one, right? Continuous, where you have the bits between a range from 0 to 1, 1 to 2. If you're going to use countable data, then 1 and 2, 1 will just be the interval. But if you have, say, 1 and 4, that includes 2 and 3. But if you say 1 and 2, then in between will be decimal numbers. Now, the set builder notation is this one. Like S is equal to a curly bracket, X, and a bar sign, and the conditions you want to build your set. And this is read as the set of S. And this is all X's, the set of S, that is all set of X's, or you can remove the set here. That could be possible. The set of S is all X's such that, there you go. So if we're going to interpret this, it will be the set of S is all X's, I repeat, to read S is equal to curly bracket S. The set of S is all X's such that, this is such that, X is an element of all natural numbers, comma, and also X is less than or equal to 5. So it means all decimals, natural numbers doesn't have the plus and the minus, right? So these are counting numbers. So it will be from 1 up to 5. the natural numbers, 1 to 5, because it says here equal to, less than, or equal to, greater or equal to. Greater or equal to 5 will be 5 up. Greater or equal to 5. Less than or equal to 5, that will be 5 and down. All right, so those are the notations. And now let's do some, let's have other vocabularies here. Universal set. Hang on. Universal set, what is this? Where is it? There. Hey, sorry for that. If I have a set of all x's such that x is a natural number and that x is less than or equal to 5, then I will have 1, 2, 3, 4, 5. Okay, so this is what the notation means. And this 1, 2, 3, 4, 5 will be in a universal set. Universal set will be placed in a rectangle. So you put all your x's here, 1, 2, 3, 4, 5. So these are the set of elements under consideration. Why consideration? Because you have a condition set in your set builder notation. If a set doesn't have no element, then you can just put a pair of braces. Like S doesn't have any element, then you can do like that. Okay. The curly bracket, like this one here, this is just a style, but you can just do a curl and then twist it at the middle. That's it. And it's the same as the braces with a zigzag at the middle. Or you can just say S is equal to phi, where phi is a symbol in set theory, where it means this set S doesn't have any element. But it's a no, no, no when you do S is equal to curly and an empty. There's no such thing as empty in an empty set, or an empty set is a subset of an empty set. So it's a double error. Why? Because this is like 0 inside a 0, 0 inside a 0. There's no such thing as like that. So when it's 0, it's simply 0. Now we move on to operations on sets. If we have operations with numbers like plus, minus, times, and division, then we also have operations on sets. And these are union, intersection, complement, and difference. Right? So these are the basic theory or operations that I want to introduce in the subject. Right, let's go to union of sets. So it says here, let A, B be sets. So there are two sets here. The union of the sets A and B is, this is the notation, A union B is equal to all x's such that x is an element of A or x is an element of B. This V here is an or. Okay, again, the union the union, hang on, oh, the union of A and B is equal to all x's such that x is an element of A or x is an element of B. If A has the elements 1, 4, 7, and B has elements 4, 5, 8, union means you have to combine them. And combining them, when it's represented in a Venn diagram, they will always have an intersection. If they don't have any intersection, then it will appear like this. Yeah, two zeros or two circles inside the universal set. And if that happens, then it says disjoint. Okay, they are called disjoint sets. Disjoint because they did not join each other. But if you have the universal and then there is a common or there are common elements, then there is union. All right. So we have here an illustration. Set A here has got 1, 4, and 7. Okay. And set B has got 4, 5, and 6. There is an overlap as you notice here. There's an overlap. And the overlap contains 4. Why? Because 4 is the common number for both A and B. And you can even see from the set themselves when they are written, then 4 is a common. So it means that it must stay or be written at the middle. Okay. Okay. So what is A union B? It can be written as A union B, A union B. Oh, hang on, it's not shading. A union B is not shading really. Okay, A union B absolute, okay, is equal to set A plus set B minus the intersection. So by numbers 1, 4, 7 plus B is 4, 5, 6 minus the intersection, which is the common number, minus 4. Then 4 here and 4 here cancels out, and the remaining will be 1, 4, 7, 5, and 6. So you have the inclusion minus the exclusion. The inclusion would be the A plus B elements, and the exclusion will be the intersection. Let's look at the set again. You have 1, 4, and 7 for A, and B will have 4, 5, and 6. So what's A union B? It will be 1, 4, 7, 5, and 6. 1, 4, 7, 5, and 6. Common numbers or common elements must only appear once in union. Okay, let's move to the next operation. And this is the intersection of sets. Let A be sets. The intersection of A and B is written as in the set builder notation. A intersection B is equal to all x's such that x is an element of A, and a while ago when we use the or, it's opening up, but when it's and, it's opening down, and x is an element of B. Look, and it means it's true to A and it's true to B. That's the intersection. The A union B is an or. Yeah, it's an or. It's an element of B or element of A. You just have to unite them and cancel common. Here you are interested of the common element. Okay, so let's plot them again. So we have 1, 4, 7 for A, 4, 5, 6 of B, and all the other numbers will be around. Say this is a set of all x's such that x is a natural number and x is, this is 0, 1 to 9. So x will be less than or equal to 9. Okay, so this is our universal set. This is our set. Yep, that's S. So it's all x's such that x will be from 1 to 9. So if you plot A, it's 1, 4, 7, and B, 4, 5, 6. We can already see here 4 as a common number. Okay. And this is the intersection. Easy peasy. Now we go to complement. Okay. Complement will be all those numbers that are not within the set of consideration. Example, the complement of A, this is A, whole A, the complement of A will be 0, 2, 3, 5, 6, 9, and 8. Do you understand? So A complement will be all the x's that are not in A. These are all the values of x such that x is a natural number and x is not an element of A. You understand? So, not element of A from here. The elements of A are just 1, 7, and 4. Therefore, A complement will be 0, 2, 3, 8, 9, 5, and 6. Those that are not within A. Okay? So these are A complement. And if we say not, if we say not A complement, the bar at the top is a not. So if it's a not A, then it will be 0, 2, 3, 8, 9, 5, 5, 6. Not A. Okay. So not A and A complement has got the same. Therefore, a not A is the same as A complement. You have to take note on this. Okay. Any other notation for not A or A complement? That's all we can do at the moment. Let's do this one. Not B, or B complement. B complement will be outside B, okay? Outside B. If you say complement, complement of B will be 0, 2, 3, 8, 9, and then 1 and 7. That is not B or B complement. Okay. If you have A union B, not A union B, not A union B, then you have 0, 2, 3, 8, 9. That's not union B, A union B. And if it's not A intersection B, not the intersection, then you have 7, 1, 0, 2, 3, 5, 6, 9, and 8. Okay? Not union B. These are all the unions of A and B. So not A union B will be 0, 2, 3, 8, and 9. Those are still inside the universal set S, but they are outside the two circles or outside the Venn diagram. I hope you have understood this one. All right, so now we go to the difference. The difference, let A and B as sets. The difference of A and B is the set containing elements of A that are not in B. So A minus B is all x's such that x is an element of A. X is an element of A. What are the elements of A? 1, 7, 4. Okay, 1, 7, 4. And then the inverse triangle is an end. And X is not an element of B. So 5, 6 are not element of B. Or this is the intersection, A intersection of not B. All right, so let's have this one here. The elements of A are 1, 7, 4. And B, they are 4, 5, and 6. So it says it's the intersection of A and B, intersection, and not B, not the complement of B. Not the complement of B means B itself, right? So if this is B and this is the intersection, then we have to include 4. And not the complement means the B itself, because the complement of B will be 1, 7, 0, 2, 3, 8, 9. So not the complement will be the B itself, 4 and 6. So what's the difference of A and B? It will be 1 and 7. Okay? So I will repeat that one. We have A, you have 1, 4, and 7. You have B, and this is 4, 5, and 6. A minus B will be A minus B minus your intersection, and those that are not B, those that are not complement of B, not complement of B. So it means B itself, because the complement of B are 1, 7, 0, 2, 3, 8, and 9. So not complement will be 5 and 6. A intersection of not complement of B. So the answer would be A minus B is equal to 1, and 7. All right, so I hope you have understood the operations, basic operations of sets. And here is the homework prepared for you. You have U as the letters of the alphabet. A would be the vowels, A, E, I, O, U, set of vowels. And B would be the set of letters in the word discrete math. So I want you to put in the braces what are the elements of A union B, what are the elements of A intersection B, the elements of the A intersection B, but not in the A intersection B. They are the complements, not A intersection B. They are not the intersections. The difference of A and B minus A, and you have to answer and provide the set. Is a subset of B? So C with an equal sign at the bottom is called a subset. Okay, is A a subset of B, or are all the elements of A in the set of B? That's what it means. Are all the elements of A in the set of B? All right, so this is your homework 3. Okay, so please write all these ones in your notebook and we will mark them when we meet. Bye for now and have a great weekend.